general exponentials and logarithmic functions. You know, there's a couple things I want you to recall before we actually get into the meat of this subject. It's just the easy exponential properties of exponents that you guys probably know. Namely these ones. At least I hope you know. What happens if I have common bases that are multiplied together? What do I do with my exponents? Okay, so here we have a to the x plus y. How about if I have an exponent raised to an exponent? What do I do?
Multiply.
Perfect. So here we have a to the x times y. What if I have a product? AB is a product raised to an exponent.
AX times BX.
Good. It's kind of like distribution, only it's not a cross addition. We only do it with a product, and we only do it with exponents here. We'd have a to the x times b to the x. If you have common bases and they're being divided, what do we do with our exponents? And lastly, for the same reason x goes to both a and the b here, the factors, x goes to both a and b here. In fact, you can use this one to prove this one. So just keep those in mind. We're not going to do any examples dealing just with those, but when we do some of these things, a few of these are going to pop up. So I don't want it to be a big surprise as, what's he doing? That's magic. No, not magic, just the properties of exponents that we can do. So, you ready for it?
Yeah.
What we're going to work on first is we're going to change an exponential that does not have a base of e into an exponential that does have a base of e. The reason is, we know how to take derivatives that involve e to the x, correct? Hello, are you with me?
Yes.
We know how to do that, we just did it. So what we're going to do now is change an exponential with a different base into a base of e. I'll show you how to do it. It's not hard, it really isn't. The first thing you have to grasp though is this. Do you understand that x is equal to e to the ln x? We usually write this property backwards, but do you understand that that is a true statement?
Yeah.
That's one of the ones we had earlier. We said, oh, hey, look, e to the ln x. How much is it? X. That was one of those properties. Well, what that means for us is that this will work for anything that you plug into x. Do you believe that?
Sure.
Yes, no?
Yeah.
Do you believe it first? So no matter what x is, so if I put a 2 here, 2 equals e to the ln 2. Do you believe that? Okay,
yeah.
Cool. So then, for anything, a, we can write it as e to the ln. Oops, my bad. I did make a mistake on that one. What should it be?
A.
Yeah. Same idea. Now we're going to be a little bit fancy about this one. What we're going to do is we're going to take and raise each side to a power. I'm going to use x. It's really not appropriate in general proof to do that since we started with an x, but I'm going to do it so that the final formula looks a little bit better, okay? So we're going to have a new x here. The new x is an exponent. So what if I raised both sides? We can do that. It's an equation. I can do whatever I want as long as I raise both sides to the same power. If I raise both sides to the same power, this side becomes a to the x. This side becomes, oh, look at that. It's property number, whatever we have over here. What do I have when I have an exponent raised to an exponent? Do I add, subtract, multiply, divide? What is it? So I'm going to have x times ln a. What I want to know is, are you okay with that? Show of hands if you're all right with that one. Now, this is exactly what we're talking about. If we have a function of x that is in, look at that, that's an exponential. It's some number, 2, 3, 4, 7, doesn't matter. It's some number raised to an exponent that happens to be a variable. If we ever have that, we can always change it by this rule. Well, okay, a to the x equals e to the x ln a. Let me show you one time so that you get the idea on what we're going to do, okay? We're basically, just so you know, we're only going to use this to be able to find the derivative, but we can practice a few times so you understand the concept here. let's say I gave you 2 to the pi, just for funsies, 2 to the pi. It's not an exponential because it doesn't have a variable in it, okay? That's actually a constant. But we could rewrite it. Let's just see where the things go. What is our a here?
2.
And what is taking the place of our x here? So instead of 2 to the pi, I could write this as, well, the e stays there. Instead of x, what would I write? ln of whatever the base is. That's exactly right. That's an equivalent statement. And you can tell, it's really easy to see that you can tell. We can move coefficients of ln to exponents, can't we? This would be 2 to the pi. E to the L, oh, that simplifies. E to the ln's gone, that's 2 to the pi. It's almost a trivial statement, but it's something that we can do. Change any base into a base of e by doing that. Any function, any exponential with any base into a function of e. Well, if we can do that, that means we can take the derivative all the time. Show of hands if you are with the idea so far. Okay, now let me show you how to do the derivative here. Let's start with the derivative of a general exponential function. So no claims about the base other than the base is not 1. If the base is 1, this is a really boring example because we always just get 1. So the base is a is not 1. So we have a to the x. Well, let's rewrite it using what we know right here. If we're trying to take the derivative of a to the x, well, that's going to be the same thing as taking the derivative of, what was that one again?
E to the x.
Good. E to the x ln a. We okay with that so far? Now, can you take a derivative of e to a function of x? Think back to what we know. We just did it last section. Can you take a derivative of e to the x? Of course, yeah. Remember, ln a, this is not a variable. This is a constant. This is like ln 3 or ln 5. It's just a constant. So this is a function of e with just really one variable of x in it. What would the derivative of e to the x ln a be? Do you remember the chain rule? We're going to use that. It'd be, what will we start with, folks?
ln a.
Okay, we're going to get that ultimately e to the, wait, hang on.
So that whole thing.
This right here?
Whole thing.
No,
ln
we
a.
start with e to the x ln a. Remember how we take derivatives of e to the x and we don't change anything about it? And then we do a derivative of what? Now this is interesting. I hope you realize this.
Product rule.
Look, I'm going to ask you about that. Product rule or not?
Yeah.
Okay. Would you do a product rule here?
No.
Would you do a product rule here?
No.
Product rule?
No.
What's the derivative of that?
3.
Product rule here. Would you do a product rule here?
No.
What's the derivative of that?
3.
It is still 3. Multiplication's commutative. It switches back and forth. So, if it's a constant times a variable, do you do a product rule?
No.
Is this a constant or a variable?
Constant.
You have a constant times a variable here. So yeah, I know it's backwards, but this is essentially saying ln a times x. What's the derivative of ln a times x? It's ln a. It's just ln a. The derivative of 3x is 3. The derivative of ln a x is ln a. I know it might seem outside the box for you because you're not used to dealing with ln a like a constant, but that's what I'm trying to get you. This is what your pre-calculus teacher and your math teacher were trying to get you to understand. That's not a variable. It's just a constant. It's a number. If you plug it in a calculator, it's going to give you the same number over and over and over and over again. Does that make sense? And a is fixed. A is your base. It's fixed. It's not a variable. So when I take a derivative of this, the derivative is ln a. Are you sure you're with me on that one? It's not a product rule. So we have e to the x ln a times ln a. The derivative of this is ln a. Let's write it just a little bit differently. This looks a little bit funky. So what we're going to do is we're going to say, okay, well, the derivative, oops. One more step in here. Let's put the ln a first. ln a e to the x ln a. Are you still okay with it? We're going to get a little bit more fancy. We're going to try to get rid of the e. Now, because we can do this, look at this. Because we can do this, well, I should go over here. Because we can do this, that means we can go back. Does that make sense? So how much is e to the x ln a equal to? Then this piece is a to the x. So we have ln a to the x. That's how you take a derivative of a to the x. By the way, this is a proof. You don't have to do this every time. This is now part of your derivative table. You can do this now. So anytime you see a derivative of an exponential with any base, whatever, I don't even care, of 2 to the x, for instance, you do ln 2, 2 to the x. That's it. That is the derivative, and we just proved it. Quick head nod if you're okay with that one. Would you like some examples here on how to do this?
Yes.
Probably, huh? We haven't done any yet. Let's keep it simple. Let's do... Let's do that. Remember, you do not need to do this every time. Now we have a formula. We've got what our derivative actually is. So tell me, ladies and gentlemen, what is taking the place of the a? In other words, what is our base here? Good. So our pattern, our formula for derivatives says, if you have a base, we do ln of that base, and then we basically get the same thing back again. That shouldn't be a big surprise, because when we did derivatives of e, we're always getting the e to the x back. Remember that? We always get the function back. Same thing here, we always get the function back. Only now we tack on this ln a. So in our case, we're going to start with what, please?
ln 3.
Perfect. ln 3, and then we're going to have, that's it. That's it, ln 3 times 3 to the x. That's the whole idea. Do you get the whole idea? Super hard? Do you see the similarity between this and your derivatives involving e?
Yeah.
It's really similar. I hope you understand that you basically do the same thing here. If you wanted this, you could still do it here. This is more general. This is a special case. Here's why it's a special case. If I did ln e times e to the x, how much is ln e?
1.
Bam. So it's right there. Okay. You are doing that. It's just it's a special case, so you don't need to show that, because ln e is 1. That's the idea. Did you get me?
Yeah.
Kind of cool, right? Okay, so let's do some more. Let's practice some of these. I want to look at the derivative of 5 to the cube root x. One thing that we're going to tack on here before we attempt this, you need to understand that the chain rule is still in effect. So if you want one more additional thing here, if we want to find the derivative of a to the u, where u is a function of x, it's the chain rule. The chain rule says you're still going to have ln a, you're going to still have a to the u, and then you would do du dx. This is via the chain rule. Are you guys okay with that one?
Yeah.
Same idea. It says, okay, L base is a, ln a. Keep this the same, a to the u. Derivative of the inside. It's just like functions of e to the x. It's only that we have an ln a in front. Basically the same thing. We cool? Let's try this then. If I want the derivative of this guy, so this is another little sub note that you gotta have. Derivative. What's the first thing I'm going to start with since I'm having a base of 5? What do I start off with?
ln 5.
Sure. Okay. Next thing I'm going to have, remember that with any exponentials, we get the whole function back again. So I have ln 5, then I'm going to put,
Cube of x.
I'm going to have the exact same thing. And then I'm done, right?
No.
Okay. What do I have to do here? Chain rule. Did I tell you we're going to do chain rule like all the time? Oh my gosh, we do all the time. That and substitutions, that's your bread and butter. So we have ln 5, that's what it says, ln 5. We have original function back, a to the u, times the derivative of what? Oh, what's going to be, what are we trying to find the derivative of? Not just x, we want to take the entire exponential function right there, the entire exponent. What is it? Can I change the cube root of x? Because I don't like to deal with the cube root of x. Good. Okay, so ln 5, calculus is done here. 5 cube root of x, and then we're going to multiply by, okay, let's see. If I multiply by the derivative of this, what is the derivative of x to the 1/3? Why don't you tell me?
1/3 negative 2x, 2/3.
Honestly, all I heard was blah, 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 blah. I'm going to imagine what you said was 1/3 x to the negative 2/3. Did you say that?
Yeah.
Okay, we're going to do a little bit more fancy pants math here. This is on a denominator. This gets to change to a denominator and becomes a cube root of x squared. Do you see it? So our final answer here would be ln 5. I ran out of room. I hate being this disorganized, but that's looks even worse. Ln 5. 5 to the cube root x over, what's going to be down there?
3 to the 2/3.
Yeah, we talked about the cube root.
X squared.
That's it. No simplification. Can't do anything with that. You're done. That is your derivative. Show of hands if you feel okay with your derivative. Good. That's great. Tell you what, we're going to do a few more here. This is really good practice for us. So, let's move back.
Whoa.
I know, right? Is it going to be super hard?
Nah.
No, not if you remember how to take the derivative of an exponential. None of these are really hard. You just have to be super good at chain rule. Not even get super good at chain rule, you're good to go. So let's talk about it first. Do we have a base?
Yes.
What is our base?
7.
So we're taking the derivative of an exponential. So as soon as you start that out, you're going to start out with what? ln, whatever your base is. So ln 7. ln 7. I erased the chain rule idea over here, but hopefully you guys knew it. If this was u, then this was u, and we just get a du dx. And that's practically it. So we have our ln 7. We have ln of our base. What's the next thing? Just people on the left over here, what's the next thing that we're going to do? Okay. So we leave that alone. We just put it right here. That's nice. Right side people, are we done? What needs to happen here? Would you do me a favor when you're going through these? I know that you have done chain rule before. Write out your steps. Okay, don't try to do these on your head. Write out your steps. It really will help you. So what I mean by that is, here's this, here's this. I want you to show me the ddx of tan 2x. I don't want you to just do it in your head. I want you to follow, I like to say, follow the ddx. Follow down the calculus. The ddx is the only calculus you need to worry about. So here's the ddx. You said, okay, we know it's an exponential. Start doing the exponential. Then when you get to a chain rule, this says, don't worry about this stuff. Here's where your calculus is. Just follow the calculus. Follow the ddx. So we're going to have an ln 7. We're going to have a 7 to nasty junk times, let's do the derivative of tan 2x. Derivative of tan 2x. What's going to be involved in that derivative?
Chain rule.
Another one. Oh my gosh. So chain rule works this way. You take derivative of function, leave the inside alone, then derivative of the inside. What's the derivative of tangent?
ln secant x squared.
It's integral.
Oh.
Integral, we're talking about derivatives here. Now you should know the derivative from
Secant
your last
squared.
class.
Secant squared.
So secant squared, do I change the inside right now?
No.
2x. And then I'm done?
Times 2.
Oh, times the derivative of the inside. That's following the calculus. That's using chain rule and saying, oh, okay, now I have another derivative and this will be my final one. What is the derivative of 2x?
2.
So we have ln 7. We've got 7 to the tan 2x. We've got secant squared 2x. And then we have times 2. I would recommend to you to put the 2 first. So we'd go over here, we'd say 2 times ln 7, 7 tan 2x, times secant squared 2x. That's the whole derivative. Now, a couple cool things that you can do, if you notice this, that's now a coefficient. You could actually make that ln of 49 if you really wanted to. You don't have to. I wouldn't, but you can do that if you want to. Show of hands if you feel okay with that one. All right, cool. Shall we do one more?
Yeah.
I think so. Yeah, one more, and then we'll have a good place to stop for the day. Now that one looks a little funky. Okay, it looks a little funky. Well, we're going to go through it. We're going to see what's what. What's the first thing that you notice about this problem that has to be done?
An equal sign. So
There's an equal sign. That's a good. Okay. I mean, as far as the derivative. So if I wanted
ln y or ln
dy dx, and I say I want you to take the derivative of x to the e times e to the x. I even said it just right then. What's the first thing that puts these together? A multiplication, which means if I'm taking a derivative of multiplication, I need a, that's the first thing. You have to have a product rule here. Do you guys see the product rule?
Yeah.
It's right there. Slapping you in the face. So product rule says take the derivative of the first one times the second one plus the first one times the first one times the derivative of the second one. You know, I know it seems a little unusual. Let's start with this side first. I want to see if you know how to do this, okay? Eyes on the board here real quick. First, are you okay with the product rule?
Mm-hmm.
You all should be. What's the derivative of e to the x?
E to the x.
Piece of cake. Does this one change?
No.
Does this one change?
No.
What's the derivative of x to the e?
E to
Now let's look at this. What's the derivative of x to the fifth? You bring down the 5. 5x to the, you subtract 1 from the 5. That works for any constant. Is that a constant?
No.
No.
Is e a constant?
Yes.
And you can do the same exact thing. So when you do this, this is e x to the e minus 1. You leave it that way.
Pretty.
You okay with that? It looks weird, I know. But does it make sense to you? You bring it down, subtract 1 from it. And then I have an e to the x. That's here. So e x to the e minus 1, it's a constant, you can do that, plus x to the e times e to the x. A couple things you can do, you could factor out the e to the x if you wanted to. So we could have e to the x, and inside we'd have e x to the e minus 1 plus x to the e. Can I combine these two?
No.
Are they like terms?
No.
Different powers. You can't touch that. Dun 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 dun. You can't touch this. Get it?
Yeah, no, but that would be
That's our derivative. Show of hands if you feel good about that one. We're going to talk about 2 more. We're not going to do them, but I want to talk about these ones. Let's see if you would know how to do the derivatives of this. Don't pack up yet, please. This one and this one. Okay, this one first. What's smacking the face right away? Product rule for sure. Derivative of x is easy. You're going to get this back again.
Yeah, that's
Derivative
chain
of this one, what are you going to need for that?
That's chain rule.
So that'll have an ln5 in it. You see it? They'll have a 5 to the 3x in it, and it'll have a 3 in it. Do you see where the 3's coming from?
Yeah. That's
Product rule, and then you're good to go. This one, what's the first thing you see?
Quotient rule.
That's a quotient. You guys remember quotient rule?
Yeah. ID low,
Minus
low
low,
D high, square root of the
minus
bottom.
ID low, square the bottom, and away we're done.
Yeah.
Right?
Oh, jiggly, yeah.
Whatever. Anyway, so could you take the derivative of this?
Yeah.
These are pretty easy ones. This is ln2 times 2 to the x. What's going to happen here?
Chain rule.
That's another chain rule. This is a 1/2 inside to the negative 1/2. Do you see it?
Yeah.
Times derivative inside, which is ln3, 3x. Feel good about it?
Yeah.
Awesome. We'll continue this next time. All right, so if you recall from last time, we're doing a whole lot of derivatives still, and we're doing derivatives that involve any sort of exponential, not simply e to the x, but now when we have a to the x or a to the u, a to a function of x as an exponent is what we're talking about. So a can be any number now, not just e. And what we learned last time was that really the e to the x, the e to a function of x, is really a special case of this. What we end up getting is an ln of whatever your base is. Well, if the base was e, then ln of e would be 1. So it was just a very special case of that. Do you guys remember that from last time? All right, so what I wanted to do was practice one. I think we talked about this one last time, but we didn't do it. Let's take a look at this, just to get our brains wrapped around what's going on here. So if we have a function of x times a function of x, and naturally the first thing we're doing is a product rule. We got the derivative of the first times the second, plus the first times derivative second. I just want to look at this one. This is, of course, pretty easy on this side. Derivative of x gives us, so we're going to have 5 to the 3x. Plus x stays the same. When we're taking our derivatives, the main thing I don't want you to forget about is the ln. Don't forget the ln of the base. And don't forget that a chain rule happens on almost every single one of these. So unless it's perfectly 5 to the x, we're going to have chain rule. So tell me what this derivative is, please.
ln 5.
Okay, so we start there, ln 5. I like it. Then what?
3x.
We get the function back.
Times the derivative of 3x.
Good. So the chain rule says we're going to have the derivative of the function of x that we have as an exponent. So derivative of our 3x is
3.
And normally we'd show the d dx of 3x and say that that's 3. Show of hands if you feel okay with that one. Now what happens a lot of times, just like before with our e to the x, because these exponentials give you back what you start with all the time, you can almost always factor things out with product rules, stuff like this. So we can always factor out our exponential 5 to the 3x, 1 plus 3x, ln 5. And that's the idea. Are you guys okay with that one? I just want a little bit of refresher because we had a weekend between doing this stuff. So it was just a little while. Are you okay with that one? So we're specifically, I know product rule should be just fine, but specifically here, we do our ln 5. Got it. We keep the function exactly the same. The exponential does not change. And then the 3 comes from the derivative of 3x, our chain rule. Question?
So when you're taking the ln 5, the 3x, you're trying to see where the 3x happens with it. Just from the step from the taking the derivative to the ln 5.
Here to here?
Yeah.
Our derivative says, and I believe I proved this last
Oh,
time.
never mind. I see it now because it's ln a times
Yeah,
a.
that's right. So we have the ln of our base. We've got the function itself does not change, just like e to the x does not change. And then the derivative of the function of x. That's the idea. Question?
I
Like
see it now.
for notation and test taking purposes, like, did you want us to factor it out on that
I'd like
last
you if
step?
you can. Yeah.
Or can we also leave it as like a 5x?
I'd like you if you can.
Factor if you can. All right.
Okay. Yeah, we should factor things if we can.
All right.
Any other questions? Good questions. Thank you for those ones. Can we move on?
Yes.
Hopefully, you feel okay on doing these derivatives of exponentials. We're going to talk about logarithms, well, not just ln, but logarithms in a minute. We'll also talk about integrals of these in just a minute. But I do want to give you one more idea before we get there. And the idea is this. What if we have a function, because we've dealt with this before. We've dealt with stuff like x, don't write this down. We've dealt with like x to the third. That's really easy, right? And we've dealt with now 3 to the x, and that's actually pretty easy. What in the world are we going to do if we have a combination of those ideas? Holy cow, did you even know that was possible? What if we have x to the x? Is it an exponential?
Yeah.
Yeah, kind of, sort of, right? But the base isn't constant. Here the base is also a variable, happens to be the same variable. How in the world are we going to deal with this one? Any ideas at all?
Natural law.
Explain natural law. There was a process. It was an idea I gave you a few lessons ago. I think it was 6.1 actually when we started this.
Use natural log on both sides of the.
Yeah, that was called something though. When we do natural log on both sides. Do you remember what that was called? Because I'm going to ask you for that on a test. And not implicit. We're going to use implicit with it. You're close. Say it again. You're so close. Logarithmic. That's right. Logarithmic differentiation. Let's see why logarithmic differentiation is actually going to work really well here. So you tell me, because you guys should know this. Firstly, Do you understand why we're using logarithmic differentiation?
Yes.
I mean, can you do that right now?
No.
No, we can't do that right now. What we can do is think of something that'll make it easier. So if we do math or logarithmic differentiation, what's our first step in doing that?
ln on both sides.
Okay, so you have to do both. So ln of both sides. Have we done any calculus yet?
No.
This is not calculus yet. So we're going to keep on going. Let's make this even easier. What does this side doesn't do much. What does this let you do?
Bring down the x.
That's why we do logarithmic differentiation here. So we have ln y equals x times ln x. That right there is so much easier to deal with. So x to the x, like what do? Do you take the x down, subtract 1? No. No, we use logarithmic. That way we can actually work with the problem. Okay, so have we done any calculus yet?
No.
So now if I want to do a derivative, what am I going to have to do?
Both sides.
Both sides, and Patrick was right, that's implicit. So we're going to do implicit differentiation with this thing. So we'll do the derivative of the left and the derivative of the right. Okay, let's talk about the derivative of the left. We've done this several times now, so hopefully we're good with it. What am I going to do with the derivative of ln x? Everybody, ln y, I misspoke. Derivative of ln y is what? Sure, you can use y prime or dy dx. I really don't care. I'm going to use dy dx here. Why do we have the dy dx?
Because you put the derivative of the x.
Chain rule, I heard that one. Because implicit deals with y as a function of x, you have to have the chain rule here. So this is our derivative we're looking for. Ooh, right-hand side, do you see it?
Product rule.
So product rule here, why don't you work on the product rule, and I'll work on it, and we'll see if we end up with the same thing, okay? That's 1, so ln x. X. 1 over x. Did you make it that far? Show of hands if you did. You got that. That's great. So we know our product rule. We know how to take the derivative of ln x. Pretty straightforward here. Not really even any chain rule. That's kind of nice. So we have 1 over y dy dx equals ln x plus 1. X times 1 over x gives you simply 1. Now, are we done?
No.
We actually have 2 more steps. The idea is we want to get this by itself, so we're going to have to do
Subtract 1 y.
Multiply by y.
probably multiply by y. So if we multiply by y both sides, we get dy dx equals ln x plus 1, no problem,
X over x.
times y. Now, do we leave it times y?
No.
This is what's cool about this whole thing. Well, we know how much y is, so with logarithmic differentiation, if you have an explicitly defined function like this one, you can always substitute that right back in and get a function in terms of x. So right here we go, all right, this is awesome. All we got to do is take our ln x plus 1, figure out how much y is equal to, substitute back in, and that's our derivative. Show of hands feel okay with that one. Interesting though, isn't it? You take something that looks really, really hard, like what in the world? I'll give you a little hint here, so a little note for you. If you have a function of x to a function of x, do logarithmic differentiation. For f of x to g of x, a function of x to a function of x as an exponent. So don't let yourself get stuck by looking at these ones and going, oh my gosh, that is nasty, what do I do? Try stuff that I taught you. try logarithmic differentiation. Sometimes that makes it easy, especially if you have function of x to function of x, because a logarithm and ln will allow you to take that exponent, move it out front, and that changes something ridiculous into a simple product rule. We can use that. Would you like to try one more? Okay, good. Well, the first thing I want to do when we're doing it, I want you guys to kind of lead me through how you would do this one. So I'll put it on the board, but I want us to all work together. I'm not just going to do it for you. So here we go. Okay, let's talk about it. If you were to see this problem on a test, what would give away what you're supposed to do?
The y.
Probably the x, probably this. If you got a function of x to a function of x, that's telling you to do something, correct? If this wasn't an x, if that was like a square root of 3, you'd still actually be good. I'm going to show you how to do one of those in just a minute. You wouldn't need logarithmic differentiation. It's a function of x raised to a function of x. That's in your head. You go, oh, okay, log diff. Let's do that. So what I want you to do right now, first step, set up that. Okay, so we all know log diff means that you're going to take ln on both sides. Just left side people, you guys over here. What would you do next? Say it louder. Yeah, absolutely. We're still not doing calculus yet. We're going to set this thing up so that we can do calculus. So go ahead and do that next step. Right side people, your turn. What up here tells you what to do now?
I'd probably move the square root up to 1/2, make it 1/2.
Okay, we can do that. We can make this a 1/2. Or we're going to do the next step probably. I'm talking about ln equals this stuff over here. What are we going to do on the next step?
Take the
Derivative?
You probably have to show that you're going to take a derivative here, correct? Because that's the question is, can you take a derivative of this thing? Whoever's phone's on, turn that off right now. So whenever we have derivative, we go, okay, we're going to take ln, we're going to bring that down. Of course, we're going to be using probably something else here in just a minute, but we want to show that we're taking a derivative. So the way we do that is just on each side, we're going to have d dx. On both sides. Okay, let's see if you know what you're doing. Left-hand side, do you know how to do that one? Right-hand side, do you guys know how to do that one? Let's set this up, see how far you can go. Go for it. So first thing, we got to do implicit differentiation. So we're going to have to deal with the left-hand side, ln y. We just dealt with that one, no big deal. Work on what you need to do on this side. Okay, hopefully it's been pretty straightforward for you. What does this side tell you to do?
Product rule.
Yeah, so we're going to do a product rule. And we already talked about how we're going to make this square root of x and x to the 1/2. That's the way that we have to work with those square roots. So derivative of the first times the second plus the first. I'm not going to change it to the x to the 1/2 over here because I don't have to work with it. I'm just going to leave the square root of x times the derivative of the second. Ooh, let's see if you remember this stuff. Let's see how far you got. Did you get this far? Cool. Did we get the 1/2 x to the negative 1/2 times ln x squared plus x?
Yeah.
Did we all get that one?
Yes.
Awesome. Okay, over here, we leave the square root of x. So we have bring down, subtract 1, no problem. Leave this guy alone. Leave this guy alone. Derivative, oh, do you remember this one? Do you remember how to take derivative ln? Shoot, you've had enough practice with it. I hope that you have, huh? What is it?
1 over x squared plus x.
Definitely is a chain rule. I heard that. That's great. So 1 over the inside.
Times.
Good. Follow the ddx times the derivative of the inside. They get really long really quick, don't they? Kind of nasty looking. Hard?
No.
Not really hard, as long as you understand the chain rule, as long as you know all these little pieces and put them together. Calculus is about pieces, putting pieces together, doing derivatives of little pieces at a time. It's not all it's about, but that's one way that we do derivatives, is by checking out pieces. So we have 1 over y, dy dx, no problem. We gotta, we can actually change this right here if you want to. Move the parts that should be on a denominator to the denominator. So the 2 on a denominator, x to the negative 1/2.
1 over 2 to square root of x.
Here's our 2, here's our square root of x on the denominator, and we have ln x squared plus x. We okay with that one? Okay. Over here, we're almost done over here. We got a square root of x. We've got, and you could even do it right now if you wanted to. 1 over x squared plus x, derivative of the inside, what is that?
2x plus 1.
I've also been noticing some sloppy notation on some of your homework. Yes, I do look through them. When you do this, this is not correct. I will mark you down, and so will any other teacher out there, for doing this. This is not right. This is right. So I know you know how to do a derivative of 2x plus 1, but you have to show that product. If you don't, what this literally says in math is that you have plus this big term plus 1. Do you guys see the difference?
Yeah.
There's a big difference there, so please be aware of that. You need to be, that's why you took algebra, so you can do things like this, you understand that. So show me you understand your algebra. Don't take calculus to finally fail algebra, all right? That would be silly. So show me some of this stuff that you know. Okay, so moving on, let's make all this one fraction. If you want to get super, super fancy, you could find a common denominator and make that one large fraction. I don't care if you want to do that, but you could do this. What you do have to do is what?
Solve for y prime.
That's important. So when we multiply by y, you're taking this entire side and multiplying by y. So multiply by y on both sides. We need to get our dy dx on the same side. I'm going to move up here. So none of this changes. We're just tacking on the y. Now this is times y. Should I leave it times y? No, we already had that down here. So what we're going to do, I'm going to erase that one. I'm going to put what y is actually equal to. How much is y equal to?
The original fraction.
You're right. And that's our correct derivative. Oh goodness. It turns out nasty, but can you follow it?
Yeah.
Show of hands if you do feel okay with that one. Keep in mind what we're doing. We kind of lose track of what we're doing in calculus when we're doing derivatives. What is a derivative?
Instantaneous slope.
Instantaneous slope, that's exact, or instantaneous rate of change is what they say. Slope of a curve at a point. That's what we're doing. here's a curve. Here's the function for the slope of this curve at any point that you want. So keep in mind what we're doing. We're not just doing meaningless math, we're finding the slope of a curve at a point. Or instantaneous rate of change. We're still doing that. It just happens that these curves are a lot more advanced than what you dealt with in your last class. We okay with this idea? Are you guys ready to move on to integrals?
Yeah.
Let's do this then. So integrals. You're going to see a lot of the same things pop up with integrals because naturally an integral is just the reverse or the inverse of a derivative. So it's the antiderivative. So when we're doing an integral of a to the u du, we're going to see that the function itself pop back up again, just like we did with exponentials involving the base of e. So if this was e to the u, we'd just have e to the u, wouldn't we? Hello?
Yep.
And we'd have a substitution if we needed one, but we'd have e to the u. Well, here we're going to have a to the u. Now, when you did an integral of e to the u du, we just got e to the, you don't need to write this down, you already have it, okay? You would just get e to the u, correct?
Yeah.
Well, what happens with a is because we have a different base here, we actually get a little extra piece. Now notice something. If you did that here, how much is that? So this is just a special case of this one. It's the same thing, just a special case of that. Does that make sense to you?
Yeah.
Okay, so we have, does it look similar to the derivative? Instead of multiplying by ln, we just have divide by ln. Very similar to other types of derivative integral relationships. And then, of course, plus c. Let's try a couple real quick. Start out with some very basic ones, and we'll work our way up to some more difficult ones. So, integral of a to the u. Well, we're going to do a to the u. We're going to keep it exactly the same, just like we kept e to the u the same. Only now we're just going to divide by ln. So this one more piece, you have one more piece now to your integration table. If you can make it fit this, you can do this every single time. Question?
If we have like 3 to the negative x, just take an interval, would that be like a chain rule? Or
You
would
do a
that be-
substitution.
Oh, okay.
So you guys got to remember with integrals, anytime, they're different from derivatives, okay? We don't have all the rules for integrals yet. That's next chapter. That you do for derivatives. So you have a product rule for derivatives, right? You have a quotient rule, and you have lots of chain rules and stuff like that.
Yeah.
For integrals, all you have is it's got to fit, or you have to make a substitution to make it fit. So if you had a negative x, right now what you'd be doing is going, oh, u equals negative x. Okay, and then you have e to the u. So if it does not fit this, you need to do what?
Make it fit.
Substitution.
Make it fit. That's right, substitution. I'll show you who's boss integral.
That's right.
I'll substitute you right out of there, sucker. That's what I say to my integrals all the time. I'm a little crazy, but anyway. So, do we need a substitution here?
No.
No, it fits perfectly. A is a constant, we have x, it's perfect. So, what are we gonna do? What's our integral gonna look like?
3 to x.
Yeah, that's it, 3 to the x. We keep it the same over.
ln 3 plus c.
That is your integral. Very straightforward. Hopefully for you. Easy?
Yeah.
Okay, so let's do a couple more. Oh, you know what? I did want to show you one more thing. I noticed this on a couple other papers that people weren't too sure how to actually do this. What if I said that instead of an indefinite integral, I want a definite integral? Like
4
this.
minus
Do you
0.
remember what to do?
And you plug in whatever value you set.
Do I need a plus c?
No. That. It gets rid of that.
Do I still need an integral?
Yeah.
No.
Wait.
An integral says you're doing integrals.
Even though your value
Don't you
is
put the
different.
straight line instead though?
Yeah, you go from here
Yeah,
to
yeah.
here. Which one do you plug in first, the 0 or the 4?
4.
Four.
Okay, so we would have 3 to the 4 over ln 3. We subtract 3 to the 0. Don't automatically make those zeros. It's not the case now that when you plug in 0, you get 0 all the time, okay? They're exponentials, so we get actually 81 minus 1 over ln 3. Did you guys see that? Common denominator already?
Yeah.
So 81 minus, so we get 80. It's a constant. It's still a constant, just ln 3 is a weird number. That's the idea. Are we okay with that one?
Yeah.
Okay, let's continue then. Are you sure you're okay with that?
Just don't make it from 0 to 4. That's what I don't understand.
How about we try that one? Let's do that. Okay, you guys should be at about the point where you're able to walk me through what you're going to do on this, this problem, this integral. So can you tell me what your first idea would be here?
Substitution.
Natural. Does it fit perfectly what that looks like?
No.
Then you have to have a substitution. What's the appropriate substitution? Would I pick this entire function here?
No.
It's a bad idea because we're going to get 3 to the square root of x, and I don't see that again. What is a good idea?
Square root of x and the
Which one?
The exponent one.
The exponent.
It's usually the inside of something. So it's going to be the exponent here. You're absolutely right. So if u equals square root of x, then du equals, remember that's x to the 1/2. So we'd have 1/2 x to the negative 1/2. Perfect. Now you can do this any way that you want. I really don't care. You can do the solve like I do it for dx, or you can do the move the constants over, rewrite this to fit this, like that one. Some of you learned one way, some of you learned the other way. It really doesn't matter to me. I'm going to show you both ways. Sometimes it's easier to do one rather than the other. Are we okay with this one?
Mhm.
So this is, well, multiply by 2, you get 2. This is 1 over square root of x. This piece is this piece.
2 du. 2 du.
Oh yeah, you're
Right,
right.
moving up.
I missed my, come on. It's not that hard to draw a U, is it? U. All right. You know what? There's one more thing that we can do. You were taught this in your Calculus 1 class as well. Occasionally, it benefits us to change bounds. Do you guys remember changing bounds?
Yeah, you plug in your integrals to the original.
We're going to do that right now because I need to make sure that you actually understand how to do it, okay? So when you change bounds, you go, all right, well, notice that 4 and 1, those are in terms of your original variable x. If you're going to change variables to u, you can also change your bounds to u's. That way you don't have to re-substitute later. So I'm going to do that right now. Here's how I like to do it. I like to write out what my x is. If my x is 4 and my x is 1, we're going to change those to u's. So if my x is 4, look at this. If x is 4, how much is u?
2.
Boom. If my x is 1, so plug it into your substitution. That's how you change it. If x is 1, u is 1. So that doesn't change. But now we get a couple, really different looking integral. Okay, so stick with me here, folks. Instead of from 1 to 4, I'm going from
2 to 1. 2.
not 2 to 1, no. 1 to 2, yes. Am I still going to have 3 to the square root of x? No, I'm going to have 3 to the u. That's right, because that's our u.
You put the 2 out.
You guys okay with this one?
Yeah.
Now, check this out. This is the other way to do a substitution. This piece is this piece. So instead of all this, I just have to write 2 du, and that's the correct integral right there. So we've changed bounds. 4 went to 2. 4 went to 2. 1 went to 1. So instead of 1 to 4, we're going 1 to 2. 3 to the u, because we made our substitution there. We got 3 to the u, no problem. Instead of a dx over square root of x, or 1 over square root of x dx, this equals 2 to u. Show of hands if you feel okay with that. Tell me what to do with these pieces. Take the 2 out. Can I take the 3 out?
No.
No, that's wrapped up. Okay, so we've got 2 integral 1 to 2, and then we got 3 to the u du.
2.
We okay with that one?
Yeah.
Can we do that integral now?
Yeah, you
It's
can.
really easy. Make it fit with the substitution. It's really easy.
You can get 2 times.
So we got a 2. We've got
3
3 to the u. Cool, I like 3 to u. And then, are we
over
done?
ln 3.
Yeah, these don't work exactly like the e, okay? So you don't just get this back again. You have to show if it's not an e, ln 3. If you forget about that, always put it up over ln of the base, and then any ln e automatically changes to 1, okay? So if you forget, which one do I do? Well, do this all the time. And that way when you get ln e, you're good to go still. Does that make sense?
Yeah.
Now, are we done?
No.
Tell you what, if you had not changed bounds, if you hadn't done this, what you'd have to do right now is instead of u, you'd have the square root of x, and then you go from 1 to 4. Since we did change bounds, we now have this in terms of u. This is all in terms of u. So we don't change back to x. We go from 1 to 2 because, hey, if those are u's and that's a u, they match up. I can plug these numbers into this function without back into x. Does that make sense?
Yeah.
Okay, so we have 2 out front. You can leave that 2 out there and multiply later. We'd have 3 to the second over ln 3 minus 3 to the first over ln 3. Let's go for it. 3 to the second is 3 to the first is 3. So
Over ln3.
so we get 2 times 6 over ln 3 or 12 over ln 3. And that's the idea. Okay, show of hands, I want to know how many people are okay with that one. Cool deal. Tell you what, we're gonna talk about 2 more. I want you to get used to seeing the appropriate substitutions. Then we'll talk about just a couple other things.
While you're writing that, just have a quick question. Is there like a checklist to figure out which set of rules to do integration is going to work for each problem? Is there like any type of methodology to keep in mind?
Yeah, the idea is look at what your function is dealing with. So if you have exponentials, you're probably going to be making it something like that, okay? So look for you're really looking for substitutions right now all the time. When we get further into this class, there's going to be a lot of different integration techniques. Right now, you're basically looking for substitutions to make it fit your integration table. That's the idea. Okay, if it doesn't fit, try something else. Now, let's take a look at these ones to get really comfortable with actually doing these integrations, or substitutions for integrations. Look at the first one, x plus 1 times 3 to the x squared plus 2x. What strikes you in this problem right now?
As a use substitution.
Exponent of x.
There's an exponent and there's a base which is a constant. So right now, we're thinking this. Hopefully, you're seeing that. Are you seeing that?
Yeah.
We're thinking this. So naturally, if it doesn't fit this, we're going to have to do, what's the appropriate substitution? It's usually the exponent. It's usually the inside of something. So if we pick that, and now we're not going to complete this whole thing, okay? But we're going to pick the appropriate substitution here. If we pick that, we'd get x squared plus 2x, and the derivative would be 2x plus 2. Does that fit that?
You can
Tell me something I can do to make it fit.
Divide by 2.
If I do factor the 2, then it does fit. So remember, we're looking for derivatives disregarding the constants, because we can always factor those constants out. Does that make sense to you? This one will work out real nice. Now, next one. Which one's the appropriate substitution? Of course, we're going to pick either this one, or this one, or this one. So which is good? Should I pick the 3 to the x on the top? The 3 to the x on the bottom, or the 1 plus 3 to the x?
1 plus 3.
This thing. If I pick this thing, 1 plus 3 to the x, du equals ln 3. Do not forget about the ln here. So when we're doing substitutions, you know what a lot of people do is go, oh yeah, this is just like taking derivatives of e, so I just get 3 to the x. And then they go, where in the world are they getting that ln 3 in my final problem? What the crap? Can't do this stupid math. I hate you, calculus. Well, no. What's the derivative of 1?
0.
Cool. What's the derivative of this? Well, it starts with an ln 3. Don't forget about that. And then 3 to the x. Don't forget about the chain rules. Don't forget about the actual derivative of things. Are you guys all right with me on this one? Do you see that this piece is this piece?
Should that have said u equals? Or,
Oh, yeah.
oh.
How about that?
I'm like
Better?
sitting here. I was like, what?
I was thinking ahead, my bad. So yeah, if I take a substitution that equal this, you're right. Thanks for the correction. du equals, well, we get ln 3, 3 to the x dx. This piece is this piece. That's gone with our du. Of course, some of you are going to divide by ln 3. We'd have a 1 over ln 3, 1 over u. Do you see how this is going to be 1 over u?
Yeah.
What's the integral of 1 over u?
Absolute value of ln.
ln absolute value u. So we'd have 1 over ln 3 times ln absolute value of this junk right there. Absolute value is not really necessary because it's always positive, but you have plus c. Show of hands feel okay with that one. I want you to work on those on your own, okay? I'm not going to give all these away for free, but I want you to see some of the ideas here. You know what? One thing, very small little thing I want to tell you too. When you're doing derivatives, and you should have learned this in your Calculus 1 class, when you're doing derivatives and you get something like this, oops, not that, we already did that. And you get something like that. It looks a little funny, but I want you to realize what's going on here. Firstly, do I have a function of x to a function of x?
No.
Then logarithmic differentiation is off the table. You do not need it. Keep in mind that no matter what power you have, if it's a constant, you can always do your normal derivatives with it. So don't make things harder. A lot of students in Calculus 2 make things harder than they really have to be. So here, this is not harder. If I wanted to find the derivative of this, it's actually really straightforward. I would bring down my power. Remember doing that?
Yes.
It's a constant. You can do that. So square root of 2. Not that. Not that one. Leave the inside alone. Why am I leaving the inside alone? What do you do with exponents when you...
-1.
So square root of 2 minus 1 times the derivative of the inside. So we get a 1 minus sine x. Bring it down. Inside alone, subtract 1. That's our chain rule. Some people call it general power rule. Derivative of inside, that's 1 minus sine x. That's your whole derivative right there, not logarithmic differentiation. So look at what you have, think it through before you get started. Don't make it harder than it is. Show of hands feel okay with that one. Good deal. Okay. Now, the next thing we're going to talk about, we've done derivatives involving ln, right? Right?
Mm-hmm.
Actually just did some a little while ago. But we haven't done derivatives that involve log. Log of some other base besides e. Well, if you think about this, derivatives of e to the x and derivatives of a to the x were really similar. We just had another ln of that base. Remember that? We were just doing it. Well, we're going to get some, like a parallel with these derivatives of logs that don't have a base of e. Now, I want to show you that right now. So, let's talk about some derivatives. Log base a. So what if we had a derivative so essentially it looks exactly the same as a derivative in ln. It's just instead of ln, hopefully you know this, right? You should know this. When I'm asking you for this, sorry, I should have had my boxes around that. Brackets. When I'm asking you for this, this is this. It just has a base of E. This has a base of E. Does that make sense to you? So it's going to look really, really, really similar. When we did this derivative, we took 1 over x, correct? That's all we did. Well, we also really should have done something. I'll show you in just a minute what that is. We should have done something about our base. That's what we're going to do here. I'm going to prove this for you via the change of base formula. Here's how you find out the derivative of a logarithm of a different base besides e. It's really not that bad. Change of base says that if you want to change the base of any logarithm, it's really easy to do. You take an ln of the top thing. I like the argument is what it is. Ln of the top thing over ln of the base. That's it. That's it. That's how you can change base. Now, if that doesn't seem really useful to you, think of one thing. Is a constant or is a variable?
Constant.
It's a constant. Do I need a quotient rule here?
No.
Absolutely not. Freaking don't do a quotient rule when you don't have to. My goodness gracious. No. What this is this is essentially 1 over ln a times ln x. We okay with that one?
Yeah.
This is not a product rule. This is a constant. So what our derivative would be, I'm going to have to erase this, sorry. Well, our derivative would be is 1 over ln a times, hey, can you do the derivative of ln x?
Or
1 over ln a times x. That's how we do the derivative. Does it look similar to you as to things we've done? Check this out. If I ask you for the derivative of, thinking faster than I'm writing, my apologies. If I asked you for the derivative of ln x, you would just give me 1 over x, wouldn't you?
No.
Couldn't you also do 1 over x times ln e? That would be the base of this, wouldn't it? How much is that?
1.
We'd have 1 over x again. We're doing the same thing. It's just we have a different base besides e. Okie dokie? Looks exactly the same. That's the idea. Now, naturally, if we have something besides just an x, we use what? If you don't just have an x, but you have a function in here, what do you do?
Logarithm.
Not logarithmic. We do
Substitution.
not a substitution, it's not an integral. If I had a derivative log of any base, don't care what it is, some function in here. Logarithm, any base, not just x, but some function in here. What do you need if you don't have just an x?
Chain rule.
Chain rule, that's right. Just a chain rule. Don't forget the chain rules. So let's see if you can put this together. How would this look?
1 over
Okay, 1 over, I like the ln, because we have, the base is not e, so we need to show that. We'd have ln of a. Times u, very good. So u's here. And then do we just stop there?
No.
No, we had chain rule, that's right, du dx. That's the idea. It's really similar. With our ln, derivative of ln, we had 1 over x times du dx. Here we have basically the same thing. We have 1 over, well, we'd have, 1 over u du dx. Here we have 1 over u du dx, but we have an ln a. Because our base is different, we just showed that. Are we okay with that one? You want to try a couple?
Yeah.
Just for funsies, make sure we got it. It's going to be really similar, so we're not going to do a whole bunch of them because they look identical to the ln's. It's just we're going to tackle on ln a lot, so we're going to see a lot of ln-a's. Did that proof make sense to you, by the way?
Yes.
Okay, this is the change of base. We just peel off that 1 over ln a, and that's where this comes from. So let's try some. True or false? This is going to involve a chain rule. True or false?
True. False.
True or false? This is going to involve. Is there something within the logarithm? So true or false? Is this going to involve a chain rule?
True.
If it's not just an x, hey, it's going to be a chain rule. By the way, when I ask that question, it's almost always right. Almost always yes, true. It's going to involve one. Now, of course, I'm going to trick you now next time and ask you that. True. And I go, no, it's false. But yeah, for the most part, if you have a function within another function, you have to have a chain rule. So let's start this out, see if you know what you're doing. If I want the derivative of y with respect to x, can you tell me what the first thing I'm going to write would be? Think of this, again, as an ln. Think of the same method. It's just instead of a 1 over something, you have 1 over an ln of the base times the something. So what would we have here? Okay, we'd have 1 over ln2. I like it, that's right, because we'd have our base of 2. That's what you're showing me. You're saying 1 over ln2 because I have a base of 2. Fantastic. So basically, if this was an ln, I would get 1 over 10x. Does that make sense? Since it's not ln, I have log 2. I'm just showing ln2. That's the change of base form that we worked with in the proof. Are we okay with that one?
Yeah.
Do we stop there?
No.
No, don't forget the chain rule. So when we do chain rule, we're going to do d dx of what? Yeah, do y'all know the derivative of 10x?
Squared.
So we're going to get dy dx. You're right, this is secant squared. So we have secant squared x over ln 2 times tan x. That's the whole show. Show of hands, feel okay with that one. Is it, see, to me when I look at it, it's really, really similar to ln. Is it similar to you as doing derivatives involving ln? The only other thing that you're going to have is what?
Change of base.
No, change rule is always going to be there. It's the change of base, that's the change of base. That's showing that to you. Okay, tell you what, let's do one more and we'll call it a day. This one will be a little bit more involved, so save yourself some space on your paper here. There's a couple things that I want to talk about before we actually do this. I want to talk about the first thing you see. What's the first thing you see if I'm asking for a derivative? What's the first thing you see? Product rule. That's fantastic. We see a product rule. What else do you see? I see a chain rule too. That's great. Now, am I missing something? If I'm missing the base, what's the base?
10.
Very good. So I'm not missing a base. If I mess up, the base is 10, okay? So I'm not missing a base here. The base is actually 10. Are we okay with that one? Okay, let's see. I'm going to have to go kind of quick because we're running out of time. Why don't you guys see if you can do this too? Start with the product rule. Go as far as you can. I'm going to do a step every about 5 or 10 seconds here. See if we end up with the same thing. So product rule. Oh, you know what? I wanted to ask you one more thing here. Can you split this logarithm up by addition?
No.
Okay, don't make up your own math. So if it's not product, you can't split that up. Or quotient. Let's check your product rule, see if you got it the same as I did. Did you do derivative the first times the second plus the first times derivative the second? Or something along those lines?
Yep.
Did you get 2x log e to the 2x plus 1 somewhere in your derivative? Fantastic. X squared. Okay, so we leave our x squared alone. Don't mess that up. Derivative of log starts out 1 over, because A, it's just like an ln, just has a different base. ln 10, I like it, because we got the base
Inside alone.
10. Leave it alone, so e to the 2x plus 1. Got that? And then?
Another chain rule.
Cool, so chain rule derivative, e to the 2x plus 1. Oh, let's see if we know how to handle this. Almost done here. So we got 2x log e to the 2x plus 1 plus x squared 1 over ln 10 e to the 2x plus 1 times, let's do the derivative of e to the 2x plus 1. Let's start with the 1. What's the derivative of the 1? It's gone. E to the 2x, remember what you do there? What do you do?
Bring it down, and then leave the inside alone.
It's another chain rule.
Yeah.
E to the 2x. Do we leave it e to the 2x? Derivative of 2x. Okay, so this is the derivative of 2x, which is?
2.
That's where a 2 is going to come from. If we put all this together, we get a lot of fun stuff. Yay.
Is that plus 2 in the exponent or just e plus 2?
Hang on, let me write. I can't do two things in one, Patrick. Hang on. 2x squared e to the 2x. ln 10 e to the 2x.
Shouldn't it be plus
I'm
1?
using the plus 1 though.
I messed up.
Oh, you're right.
Okay, hopefully I did that right. I just did it really quick. So let's see. We got product rule, derivative of the first is 2x, we bring this down, I think I accidentally moved my exponent up here. We've got, take the second one, this is 1 over ln 10, leave the inside alone, derivative of the inside. Cool, we got, derivative inside is another chain rule, e to the 2x times 2, put everything together, and that should be our derivative. Did you get that same thing?
Yes, sir.
Awesome.
They're all 6.4.